This podcast is brought to you by the Albany Public Library main branch and the generosity of listeners like you. What is a podcast? God, Daddy, these people talk as much as you do. Razib Khan's Unsupervised Learning.
Thanks for listening to the ungated version of the Unsupervised Learning podcast. If you want to read some essays on some of these topics, please check out razib.substack.com. Again, that's razib.substack.com. Thank you.
Hey everybody, this is Razib Khan with the Unsupervised Learning podcast. And today I am here with Davide Piffer, who is, some of you, actually a lot of you probably know him from his Substack, piffer.substack.com, and he also has a website, Davide Piffer. And the reason I'm talking to you, David, is because you've been putting a lot of posts up. I want to talk to you about your posts on ancient DNA and pigmentation. I thought it was super interesting. You guys should check them out. After this podcast, after listening to the whole podcast, obviously. But before we go there, before we talk about ancient DNA and what you are finding, what you're looking at there. I guess the main thing is, can you talk about what you're interested in and, what a polygenic score is or a polygenic index is and how that works first, just in terms of the mechanics, before we talk about kind of ancient DNA and then what results you found?
So I've always been interested in studying genetic variation between populations. This interest of mine started when I was a high school student and I read Cavalli Sforza's book. I think it was just had been published, the Italian version, History and Geography of Human Genes. And I read the Italian version, of course, and I remember looking at the maps and thinking, wow, this is really cool. They had maps of Italy, France, and general all over the world. But this was like a very primitive. It was cool, but it was ahead of its time. But it was primitive because it was based on just a few genes. Now we have like much better data, and also much bigger data sets. And we can also, on top of that, we also have these polygenic scores. So not just Ancestry, genome-wide Ancestry, which is what Cavalli Sforza and a lot of geneticists have been using for many years. But in the last 15 years, scientists have started building these polygenic scores, which are a sort of genetic score that is built using a genome-wide association studies. So, like genome-wide association studies, they study a phenotype, a trait, with large samples of people. Then they correlate the allele counts. The allele, the number of alleles within each individual, to the values of a trait. So, for example, for height, if we find some alleles are correlated to taller stature, we assign a positive effect depending on the correlation, the effect size we find in the GWAS, and then we sum all these variants together to get a polygenic score. It's a weighted sum of the frequencies and the effect size, in other words. And this index is has predictive accuracy, which varies a lot depending on the phenotype. But for height, he reached about like 50%. And for IQ, depending, of course, there is this HERA site, which is, I think, what was that, 25? And then there is a educational attainment reached 15-20%. Then we have like other traits that have much lower values. So I try to focus on the best studied phenotypes where we have larger sample sizes and a lot of GWAS significant hits for my studies.
Yeah. So, you're talking about like allele counts and all these things. I mean, obviously, this is new technology. Methods that could not be done. You talk about Alal Cavalli's history and geography of genes, which was published, well, I think 1995, 96, something like that. It was a while ago now, right? And you said there weren't that many genes, and I would like the listener to know, there weren't that many genes. There was fewer than 100 genes, really, in most of those analyses. Basically 100 genetic positions, 100 variants. And when you're doing analyses of variants, when we're doing analyses of variants now, genome-wide SNP arrays will have like 500,000 positions, right? So we're in a whole different world. Whole genome sequences obviously have 3 billion positions, of which about 4.5 million or so in the average individual will be a polymorphism. And so, when you're talking about polygenic scores, the only reason it's possible really is because of a change in the amount of data in terms of the scale of the data we have, right? Like in some ways, I think people can think about maybe polygenic scoring as a little bit like regression, like expanding it out with all of these different variables that you're weighting, and you create a composite output index. So it's really not it's really not that complicated. It's just that we have the data now. And so you just choose to look at the data. Now, it's one thing to look at data on height. You can measure people, they're alive. And even if they're dead, if you have good skeletons, you can actually measure them too. And then, height in contemporary populations, obviously you have good quality data because you have the SNP array or you have whole genome sequences. So what you're doing, though, is looking at polygenic scores. So we're going to talk about pigmentation. I think you've done educational attainment, a bunch of other quantitative traits. These are traits you cannot measure in ancient populations. You cannot measure a Mesolithic European's educational attainment.
Yeah.
They never had an educational attainment. But you also usually cannot measure. You can kind of see some pigmentation. I do have to say, it's pretty clear that a lot of the old stuff, when they said, oh, like this person has light hair, when it's like a 5,000-year-old, decomposed or desiccated individual, you're not actually getting a lot of times the correct hair. I think it's pretty clear, actually. So when it
Also
comes to
the skin,
pigmentation,
like the skin, it's not preserved for
yes.
many
Yeah, the skin is also discolored,
Yeah.
so you can't get good phenotypic measures on that. And then also there's the other thing that I want to bring up, which is the quality of the genomes. So, obviously, you have a couple of issues here, but I think the primary issue would be, there's two issues that I guess I want to bring up, like contamination, and obviously the degradation of the DNA. And so you get like a lot less markers back, even for a polygenic score, which is super important. And then in terms of contamination, you can get the wrong result. Now, I will say, when we're talking about pigmentation, I will say there's a paper, and I tweeted about this, paper of Andronovo samples from like the Altai in 2009. And that paper is used to show how pale the early Andronovo are. Okay. When like later samples came out, they didn't really match that. If you look at the frequencies of like blue eyes and blonde hair, they're suspiciously close to modern Russian frequencies. Okay, so I'm just going to say, I think that was contamination, and it's actually pretty well known that a lot of the older ancient DNA literature, including a lot of Svante Pablo's work, some of it is explicitly known as contamination, but
Yeah, like in the
on top.
for example, you get a lot of contamination as well.
Yeah. So these are issues. Like, how do you deal with them? Like, how do you think about these in terms of your analyses? Because they're not trivial.
So the data quality in terms of the DNA degradation affects the depth of coverage. So how many sequences are retrieved. So the coverage is the percentage of the genome that is actually sequencing, and the depth of coverage is the average number of times each base the DNA is sequenced. So what the DNA data comes with depth of coverage information, which gives us a reliable measure of DNA degradation. So I always add this measure to the regression. So when I run the regressions with the polygenic score as the dependent variable and date, which is years before present, Latin geographical variables, and then I also add coverage to take into account the quality. I should also say that recently I also found another metric because the genomes I'm using are actually imputed. So I've actually imputed genomes using Glimpse, which is
Wait, really quick. I do want to. Tell my listeners what imputation is, right?
the imputation infers the missing data based on the nearby genetic variants. So there are algorithms that are very computationally intensive, but they enable you to assign a probability to each allele at the genomic positions based on the nearby SNPs or genetic variants. So instead of saying, "Oh, this SNP, this GWAS SNP is missing. I'm not gonna count it for the polygenic scores." I used the imputed variant. So of course, each imputed variant has a different probability. And in my more recent paper on the Industrial Revolution, I also used the genome imputation probabilities to actually account for this imputation error or variance. And I added this to the regression. It's strongly correlated to coverage, but it also adds some signal. To answer your other question about the contamination, I don't directly take that into account. I check the papers that come with the genomes, and I usually they exclude the samples that have too much contamination from the downstream analysis. They, yeah.
Well, okay. So let's take it as a given. So actually, I do have to just with the imputation. One thing that I guess I just want you to address real quickly is you have Mesolithic Europeans, for example. There's no population that's genetically like them, and so in terms of imputing, because you have to have the reference panels that are high quality, right? And those are presumably modern samples. So you're imputing the variation of modern samples into, say, a Mesolithic European. How do you address that question?
Yeah, I actually use the 1 kg 1000 genome samples, and I think, of course, the imputation accuracy will drop the further the ancient samples are from the modern samples. So there will be more error in the more ancient data. Yeah, I followed. I'm not an imputation expert, but I use Glimpse too, and they recommend using 1000 genomes for ancient genomes imputation. But of course, with Mesolithic samples, you get noisier data. They're not necessarily biased. It's not gonna necessarily be biased in created bias in the polygenic scores, but
Mm-hmm. Well, I guess what I would say is, doing the pairwise FST, looking at the genetic differences, Mesolithic Europeans are genetically distinct. They're not like any modern populations. On the other hand, the pairwise FST, the genetic differences, allele-wise, will be lower than between, say, modern Europeans and East Asians, a little bit, probably. So you could probably use that comparison to figure out how much a polygenic score portability would degrade, right? I mean, it wouldn't be totally unpredictable, especially when it comes to pigmentation. And we could talk about that later, because you've done a little work on just portability of polygenic scores, which are there's been a lot of issues about the portability of polygenic scores, but a lot of them actually happen to be African, non-African, because of linkage disequilibrium, and just the genetic distances are greater between those populations. The degradation within Eurasians is a lot less, I would say, but I mean that's kind of a minor technical thing. I really want to get to, I guess, the trait. So I'll talk about high risk plex. Tell the listener what it is, and then talk about why you were interested in this.
Yeah. So Iris-Plex is actually a scoring method based on allele frequencies that assigns the probability of each eye color based on the combination of different alleles that affect eye color and hair color. I didn't use Iris-Plex because Iris-Plex is not public. It's a proprietary algorithm. I used GWAS of eye color and hair color. With hair color, it's easier because hair color is more polygenic than eye color. So, and there is a good GWAS of hair color that I used that. And for eye color, I used I used two genes that they're not perfectly correlated to Iris-Plex, but they're very strongly correlated to Iris-Plex. So I use those because the Iris-Plex is not published.
Yeah. So I mean, so you have skin color, you have skin color, or hair color, and eye color. I will say the eye color ones are very, very powerful in my experience in terms of the predictors. It's not like as polygenic. I mean, like a lot of times you're just looking at variation, not necessarily dichotomous, but like obviously blue versus non-blue, that sort of thing. Although some of the better newer methods now can get like spackling and various other things. You get the phenotype pretty good, actually. I will say it's pretty good on my kids. They have variation of eye color, and because parents are obviously different, or not obviously, but they are, and so the prediction is actually perfect. So these forensic reconstruction methods are really good. And they're used in criminal cases all across the world. So this is not just something that's used in an abstract, intellectual, scientific way. They're tried and tested, and the panels are pretty robust that way. And so, the key issue, and I did actually, the listeners will know this, I did write on a paper, I think at an Italian lab, actually. And you're actually based in Italy. So I don't know if it's coincidence or not. But they used probabilistic methods, Bayesian calling methods to improve the information yield that they get from their genotypes, and they got a very similar result to you, actually. So we're talking about,
I read that paper.
Good.
Yeah.
Which is good. They should get the similar result to you because
that's
I
read that actually after I published my blog, and I was like, that's cool. Someone's we validated each other.
Yeah. That's what I'm saying. So it's basically a double validation. My friend,
the piece I used where I found this other ancient genome paper where they were trying to infer the eye color, and then I looked up the SNPs they were using, and then I used those. So yeah. But it was another paper. It was not this Italian paper, but I also know about this one. Yeah. Is there one where they show the acceleration in the pigmentation over the last what?
Yeah. So I mean, I guess talk about your major finding, and then we can get into the details of how admixture and selection work and all this stuff like that. Talk about it and outline period by period so that the listener, because obviously hopefully they'll look at your Substack after they're done listening to this, but obviously they can't see anything. So
yeah, there are. I wrote quite a few Substack articles on this. So one is on blonde hair, the other one is skin color, the other one is eye color, and the other one is about the four lineages for races of Europe. And what I do is I check the time trend. So it's a time series model. I check my samples span from 40,000 years ago up until a couple of centuries ago, and they come from uh, Western Eurasia. I don't say Europe because there is also samples from Anatolia and Iran, so Middle East. And so what I find is what I do. I compute based on the genomes. I use admixture, which is a software that an algorithm that unsupervised algorithm that estimates the ancestry components in your sample. So something the ancestry components that kept popping up in different samples were one was mm, uh, more common in steppe, um, Pontic Caspian steppe people. So Yamnaya, Proto-Yamnaya like people. And then there is this ancestry component, which is Mesolithic Western Europeans, hunter-gatherers, WHG, which was which is still a bit common more common in Northern Europe now than in Southern Europe. But in the past, it was also present in Spain and in Italy. For example, the Villa Bruna sample is considered like a Western hunter-gatherer. And then you have Anatolian farmer is also very common, especially in Southern Europe. Southern Europe has a big Anatolian farmer component. These are like the people that spread agriculture to Europe, and they came from Anatolia. Then there is also another component which is a bit less prevalent, but you can still detect that, and it comes from further southeast. So it's distinct from Anatolian. It's um, Mesopotamian, southern Lebanon-like. Although I'm still not sure whether sometimes it also peaks in Iran, and so I'm not sure how to actually interpret that. If it's like more like Iran or Iraq. But it's what matters is this distinct from the Anatolian one, because some studies also they lump them together. They lump all the Middle Eastern components into the Anatolian one, but in my models, this was like a separate component. And so I used, when I analyzed the effect of ancestry on phenotypes, I used both the ancestry components referred here via admixture and the cultural labels. So the ancient archaeological studies, they provide the labels based on archaeological context and dating. So, for example, you have the Afanasievo, as you said, or the Villa Bruna, which is Western hunter-gatherer, or the Oberkassel also. Oberkassel samples from Germany, they are like Mesolithic hunter-gatherers. And so I analyzed the impact of these categories. You can say it's like cultural, ethnic labels, archaeological labels, and also the more abstract admixture components. So what I found was that, for example, this thing they call the Aryan or steppe paradox is that Yamnaya people were not the Yamnaya people, which are thought to be the ancestors of Indo-European speakers that spread Indo-European languages in Europe and in Western Asia. That these Yamnaya people, they were not blonde and white and light skin. Actually, the frequency of blonde hair was lower than among Anatolian farmers, and their skin was definitely darker than modern Northern Europeans. It was about um, the same color as Western hunter-gatherers and Anatolian farmers. So the paradox is this genetic component is very common among modern Europeans, so Irish, Scandinavians, British, Baltic people, and these people are very light skinned with there's a high prevalence of blonde hair and blue eyes. So when people think they say talk about the Aryan look, for example, on social media or even some pop scientists, that is actually not due to the Proto-Aryans or steppe people, but it's actually something much more recent. So the depigmentation happened in the last 10,000 years, but there was an acceleration starting with the Iron Age. Starting with the Iron Age, people started, the skin color of people started, at least according to the polygenic scores, it started getting much lighter. And if you would think about this, like during the Iron Age, the Celtic people, that's when the Germanic people were forming. Also the Italic people. So and the difference we see today between the skin colors between different European groups are very recent actually, and they are not due to steppe ancestry or Yamnaya or Aryan migrations. They are due to recent selection, and the same happened to with hair color and also blonde hair. Blonde hair went up in frequency over the last after Bronze Age. Um, and eye color is a bit different case because eye color was already uh, not common or was not rare among Western hunter-gatherers, Mesolithic hunter-gatherers. So Mesolithic hunter-gatherers had like dark hair and a lot of blue eyes. But of course, the frequency of blue eyes went up also in Northern Europe during the Iron Age. Yeah,
Yeah, so I mean, let me just jump in here. The earlier ancient DNA, polygenic score aside, like you can do the RCA2, HERC2 gene complexes where most of the variation for blue versus brown eyes and Europeans is, and basically, what you're alluding to here is when in 2014 the first ancient genomes from Mesolithic Europeans out there for Spain, the Lebrana samples show up. To everyone's shock, maybe not everyone's, but yeah, pretty much everyone. They were predicted to have blue eyes. They have the haplotype that is predictive in the homozygous state to have blue eyes, but their skins and their hair are predicted to be relatively dark. Now, there's arguments about how dark they are. Some of the reconstructions are quite dark, while others are less dark. I think it's plausible that they were as brown as me. That's possible. I probably not like sub-Saharan African. Probably no lighter than, say, an Inuit. You know what I'm saying? Like,
Yeah.
Siberian Arctic people, but definitely not like modern Europeans. Definitely even not like modern Southern Europeans. When you look at the scores, they're just like too many, ancestral or not ancestral, but you know what I'm saying? Like the pigmentations that in the high-risk plex that are just like coming out dark, Now, there are different genetic architectures in East Asia, but, East Asia is also genetically has a different history, which Europe has not had. So I think you could probably draw some conclusions, but we need to just couch it in terms of how extreme people get, right? And so in some parts of Western Europe, you have extremely high frequencies of these OCA2, HERC2, derived allele haplotypes, these long haplotypes that cause blue eyes, right? And so the Neolithic farmers show up. In places like Southern Europe, the fraction drops rapidly, but also in Northern Europe eventually, because the Neolithic farmers did not have high frequency at all. They have very low frequency. There are some individuals in the ancient DNA record, even in the Middle East, that did have that blue eye allele, but it was low frequency. And then what happens, in the Bronze Age, up in the Neolithic, Bronze Age, etc., is the frequency starts going back up. And there's evidence for natural selection in some of the statistical tests, like, in terms of the less thorough analyses that have been done focusing on, very, very specific genetic positions and whatnot. And, there are some population, depending on how you scale the population, there's some populations in Northeast, like in the Baltic, that have blue eyes as high of a frequency as Mesolithic hunter-gatherers, right? And so, in a way, this population, not only was it genetically distinct because, modern Europeans are not like them because they have Neolithic and, Caucasus forager and, considerable Siberian ancestry through the Yamnaya, but also like their physical appearances was quite distinct, and that just shows up in the data, and it's somewhat different than the skin and the hair, which show a consistent, I guess we would say monotonic trend, whereas with the blue eyes, it's more like a U curve or a V curve. Drop goes back up.
Yeah. And in the case, the blue eye is no linear because, as we say, that there is a relatively high prevalence among the Mesolithic Western hunter-gatherers. Then it drops due to an Anatolian farmer replacing them. Then it goes back up due to selection. So the Yamnaya didn't actually bring this package, blue eyes, blonde hair, light skin. Also, the lactose tolerance gene. It was very almost non-existent among the Yamnaya, but then it also went up a lot among Northern Europeans because of cultural, pastoralism and who knows what. They speculated about immune culture. Not sure exactly why it went up.
Yeah. I mean, maybe we can talk about selection later because that's a whole different question. So, when it comes to these traits, we've gone really far with the prediction, obviously, in terms of just like looking at the characteristic and using genomics to, figure out the correlations, and from the correlations you can figure out what the output, prediction phenotype is, what the and you can also detect to some extent that it was a target of natural selection, that those genes were the target of natural selection. But, to talk about what the exact adaptive pressures were is like a whole different game, right? So, we'll table that for now. I guess in terms of like, what you found, were you surprised? Like, I think, I wasn't surprised, partly because this was pretty clear in the data, even though it wasn't very robust. Okay, I'll tell listeners how like I figured out this had to be. The Estonians have very large, as you know, David, they have invested a lot in genetics. They have large ancient DNA sample set in the Northeast Baltic, partly because of climate and partly because Finland, Estonia, especially Estonia, has invested in genomics. You can just do a simple like pairwise comparison between the Iron Age samples and modern Estonians, and the difference is just too great. And they're genetically the same at that point. After the Finnic people had already arrived, the difference is just like too great to be coincidence. And so I knew like immediately, and like I used it. That's an extreme case. That's where the frequency of blue eyes right now is the highest in the world, and so obviously it's going up against like it's going up against the allele frequency limit in terms of like 85, 90%, whatever are the derived frequency. And in the Iron Age, it was definitely not like that, right? And so what you're seeing with your data, though, is you look across all of Europe, across many, many periods, and it's the same consistent trend, right?
Yeah, there is a slow increase during the Neolithic and the Bronze Age, and then it starts not exactly, but approximately around when archaeologists date the start of the Iron Age between 2.8 and 3,000 years ago, depending on where you look at. You see a sharp acceleration in the skin color, lighter skin color, and also the blonde hair. Let's say genes to simplify SNPs, fetuses of genetic variants. And it's interesting why the Iron Age would do this. I personally don't really, I don't know. It could be population density. What I can say is that there is not something when we look at cognitive traits like education. The line, the time, the trend is much more linear. We don't have this knot. I tested the knot with the hinge regression, and it's highly significant for skin color at 3,000 years ago. So there is actually the slopes are significantly different. But for education, like you get this knot at about much earlier, like 1,000 years ago, when the people transitioned from hunter-gatherer to farmers. So in the case of cognition, it's like more like farming, population density, and non-nomadic, settled population patterns. Whereas with pigmentation, it's more like the irony is this. And if you think about that, like I was thinking about this, like it was very fast because like the Romans were already, ancient Romans were already commenting on like Germanic or Celtic people having lighter eyes and skin than them. But they were not separated for that long. It was like already 2,000 years ago. They were already, this difference were already present then. Or even though like the Germanic people evolved mostly from the Yamnaya in the Bronze Age. So the Bronze Age, when the Yamnaya people replaced the Neolithic farmers in Germany and Britain, about 4,500 years ago, and then so you have like 2,500 years in this so we know these people were dark, and then in 2,500 years you have already completely the phenotype has completely changed because the Romans were already commenting on these people with red hair and blue eyes. I guess back then also they were not as light as now, but they were already lighter than Southern Europeans.
Mm-hmm. Yeah, I mean, one thing that I would say is, this is probably Yosef Lazaridis' work, but I mean, I think it's been pretty robustly confirmed. There were theories that the Mycenaean Greeks, were kind of Mycenaean Greeks and classical Greeks were a different race, and they were replaced by Near Easterners and stuff. And there is some admixture to Greece, but there's more Slavic, last I checked, than Levantine into modern Greece. And so the modern Greeks are actually probably paler, just looking at the ancient DNA, than the ancient Greeks. But there's all these, references, in the Iliad to people with like red hair, bright hair, and blue eyes. And, the simple translation is that they're, blonde, blue-eyed people. But, there were other people that said, well, what they think is like light eyes and bright hair might not be what we think is light eyes and, bright hair, in terms of like, the English translators, in England have very specific. And, I will say, like, I have a friend from Finland, and she has, what in the United States we would call dirty blonde hair. But she just said in Finland she would just not be considered blonde at all.
Yes.
My point there is like how you refer to something actually is pretty dependent on context. And I think these sorts of results should make us update some of our perceptions of what people look like just from the textual references.
Yes. So it's possible that the ancient Greek and Roman writers were actually calling blonde what was lighter than that, right? On average. And but actually, it's interesting because there was in ancient Rome there was also a change that was due to immigration, because in the Iron Age, Rome Iron Age, the people had more blue eyes and blonde hair than in later years, because in Imperial Rome there was a really large influx of immigrants from Greek and Syria, so the phenotype changed, and this is actually matched in the genetic data.
And so, okay, so you're finding that the changing is going into the Iron Age. I mean, is your assumption that this selection continued down into the modern period? Because I mean, obviously, the statistical power is, in terms of selection tests and stuff like that, starts to get a little wonky when you go very closely. But I mean, why would it just stop during the Iron Age, right?
No, I didn't stop in the Iron Age. It actually, the my data gets sparse after the Middle Ages, but I've actually got a lot of genomes from the Middle Ages. So the light skin, and blonde hair, blue eyes peaked in the Middle Ages. So the selection continued up until at least until the Middle Ages.
Yeah. So I mean, it's interesting. So I guess the question here is, we haven't talked about what the selection was like. Okay, I'm gonna. All right, I don't want to. You know what? Like, I've had some issues with my old acquaintance Peter Frost about some of his writings lately, and I don't want to pick on him, but I did read his older stuff about sexual selection. It was he had a complicated model, in my opinion, of like high latitude foragers and sexual selection during the late Pleistocene, during the Ice Age, and that's why Europeans have diverse pigmentations. That's obviously just wrong, because one, those people are not the ancestors predominantly of modern Europeans, at least in full. And secondarily, just all the data show that the selection is very recent, right? So that model of like Ice Age sexual selection is at least falsified, right? You did find, and
or maybe from blue eyes, you can say, this was a thing for Mesolithic hunter-gatherers, but yeah, for like blonde hair and skin color, you can rule that out because it was much more recent. Also, yeah, the blue eyes prevalence is more than Europe is not equal that Western hunter-gatherer component, which is only like 10%, 15% in Northern Europeans.
yeah,
Yeah.
and some of that is also from the Yamnaya as well, I think. But I mean, in Britain it was totally replaced, apparently. Like some of there's forager ancestry in like, say, like Iron Age Britain, but basically when I've read the literature, talked to the people, they're basically like all of that forager ancestry is actually admixture from like in Southern Europe and then in Germany. So, for example, just a minor note, but there's actually like almost no forager ancestry directly from, say, Cheddar Man and those people in modern British, because every single time they expanded, the replacement level was pretty high, right? So the admixture was like, early, and then like in a later, like middle Neolithic pulse during the Neolithic hunter-gatherer resurgence. But setting that aside, you did find that there was an individual in Gotland. I think it was Gotland, early, like about like 8,000 BC, almost like 10,000 years ago, that had blonde hair and blue eyes. So this is an individual in Northern Europe, right? Individual in modern day Sweden, in the Baltic. Yeah. And so this individual, like these population of Scandinavian hunter-gatherers were the palest at that period. And they're a mix of about 40% Eastern hunter-gatherer, 60% Western hunter-gatherer. So you had an Eastern hunter-gatherer that came over the top of modern day Scandinavia through the Finnmark, and then you have Western hunter-gatherers coming up through Jutland, through Denmark, up into Sweden, Norway, etc. They mixed, and they created Scandinavian hunter-gatherers who had lighter skin. Some of them had blue eyes, like Western hunter-gatherers, and their hair was generally dark. But like this individual is the first blondish, maybe blue-eyed, light-skinned person in your data set, right? And I think that the Italian paper that I reviewed also said the same thing.
Yeah.
And so, I mean, it's a little suspicious to me that the first individual that looks like this, like, part of this is, like, there's a lot of data from Northern Europe because of preservation conditions,
Yeah.
and also of things like Eski Willerslev's Geogenetic Center is in Denmark. But setting that aside, it's a little suspicious that the place in the world that has the highest frequency of depigmentation
Contamination.
was also the first place, you know?
It could be,
And that was also a totally genetically different population.
yeah, it could be contamination. Like one case, it's not enough. We need like more data.
Yeah. That's fair. Although I think we know that the Scandinavian hunter-gatherers overall were paler than EHG. We have enough samples, I think, that they were paler than EHG and WHG. Also, like, they have some weird genetic patterns which are not found in modern Europeans. So they have the derived frequency of EDAR, which is found in East Asians. So that's, I mean, unless there was an East Asian like lab tech in in the lab in Denmark. I think these are the Danish sample. They were in the Geogenetic Center. They were analyzed, but
one thing I found
sometimes, just for the listener, I have heard in some labs they do things like that where the lab tech is like, they will find an Asian or African or Middle Eastern lab tech if they're doing, say, like Northern European samples, because contamination is very obvious then.
Yeah, one thing I found was that latitude, and when you add latitude to the regressions, latitude after you control for time, latitude has a positive effect on blue eyes, bone hair, and skin pigmentation. Also height. So each genome, ancient genomes, has a latitude based on where it was found. Yeah, the bones were found. So latitude, like further from a northern latitude, the further away you are from the equator, it predicts pigmentation net of the time effect. So it fits with what you said about the Scandinavian hunter-gatherers. Because of the UV radiation, so we know the mechanism where low UV radiation it makes your body synthesize less vitamin D, so you need lighter skin to be able to produce more vitamin D. So it's higher latitude, you will have higher polygenic scores for this trait. In another way, this actually validates with the polygenic scores because this shows up even after you control for ancestry. So we know that these traits are correlated to in modern populations. We know that for the further north you go, the lighter the skin and the hair in the eyes, we can see that we have statistics based on phenotypes, not just genotypes. And so when you look, when I checked the ancient DNA, I found the same based on genotypes. So this, of course, not conclusive evidence, but it provides boosts the validity of using these polygenic scores in ancient samples.
Well, so I mean, I think the results. A lot of food for thought. The skin color results are really interesting. So you've been looking at other polygenic scores, like things for height, and I think you looked at education. Some of these have been published, and there has been controversy, obviously, about the publications, and so a lot of this stuff is pretty politically incorrect, right? Which I don't really want to discuss that because it's just not super interesting. People can look that up. But where are you going to go with your posts on your Substack? Because you got a lot of great content out there. There's free stuff, there's paid stuff. And like, I mean, what's your? Do you have a plan, or do you just like, hey, I'm interested in this stuff, I'm going to post it?
Yeah, I just post. So most of my, no, not most, but many of my posts were actually about the papers I did. So I didn't just digest other people's papers. And was like look and give my own comments and interpretation. Sometimes I do that. I read a cool paper, usually new one, And then if it fits with my interests, I write about that. But a lot of times I write about what I'm actually studying, so my own work, my own research. So I write about stuff that I feel like I can provide something that other people cannot, because I'm working on it. So it's something original and something I'm familiar with, have expertise in, and other times. So they're not. I don't write just based on people's requests. They're like, it's based on my own interests and my own interests, but only if it's something I feel like have something original to say. Yeah.
Mm-hmm. Yeah. No, for sure. Well, I'm gonna, obviously like a link to the posts, and link to your Substack. People should check that out. They can also follow you on Twitter, although you're not. I mean, you don't tweet all that much. You tweet some, so I'll link to that. It has been great talking to you. I hope people check out the posts. And you have we're recording this before Christmas. This will be posted actually after Christmas, considerably after Christmas. So the listener will be hearing this in 2026. But I want to wish you a Merry Christmas, and it was great talking to you, man.
Merry Christmas to you too, and everyone.
This podcast for kids